Happy Thursday. We're almost at the end of another week, which is awesome. Just a reminder, tomorrow we don't officially meet for class. I just want to do a check-in, see how everyone's doing. I want people to be able to get some of their other work done. I know a couple of students have mentioned that their other teachers are also assigning a lot, and I had signed a lot kind of at the start. So it's going to start kind of balancing out for me, I guess. I haven't really given as much this week in terms of assignments. I'm going to keep it that way for this week. Next week I might give one or two small things of just being like, show me 2 problems to make sure you're practicing the skills. And then from there we'll see what happens. So again, tomorrow is just the check-in. Stop by if you want to. I'd appreciate actually having video on. That'd be great. We do miss faces. This is a really trying time in life, and anything we can do to get some normalcy would be wonderful. So for today, we are looking at matrices. And we are going to be continuing what we've been doing in 8.1 and 8.2, but kind of in a new format. And the reason for using matrices is that sometimes data is better shown in a tabular format. So I have 2 tables right now that we're going to look at. So the first one is the amount of calories burned based on 3 different activities and the person's weight range. These are all just numbers that go along with it. And then the second one is distance in terms of miles from one city to another. If we wanted to convert these into a tabular format, we would create what's known as a matrix. We denote a matrix with hard brackets. And then all we need to do is copy the entries by row and by column, or by column. Usually we do this by row. So I'm going to go, my first entry in my top left will be 156, then 183, then 204. So all I'm doing is putting in the numbers. I'm not putting any units with them. So then row 2 will be 267, row 2 column 2 will be 315, row 2 column 3 will be 348. And then row 3 column 1 is 276, row 3 column 2 is 345, and row 3 column 3 is 381. For our second data set, I'm going to wait to draw my hard bracket. So starting at row 1, we have 325, then 465, then 440, then 650. Row 2 column 1 is 250, row 2 column 2 is 300, row 2 column 3 is 415, row 2 column 4 is 295. And last but not least, row 3 column 1 is 470, row 3 column 2 is 375, row 3 column 3 is 490, row 3 column 4 is 285. So I just removed kind of like the headings, you could say, from my tables and just turned them into an array of numbers, which is known as a matrix. When working with matrices, we count rows. I'm actually going to try something new. Not really new, but just smarter. I'm going to start actually typing this out. So when working with matrices, we first count the number of rows, then the number of columns. So for here, I need to go check this. It's done. Go back to this one. Our first matrix, well, we have rows is going up and, well, rows are the horizontal entries. So you count them by going up and down. It's weird to think about because columns run up and down, but to count rows, we count from top to bottom. So rows, we have 1 row, 2 rows, 3 rows. So this is a 3 by, and for columns, we have 1 column, 2 columns, 3 columns. So this is a 3 by 3 matrix. And I'm going to write a second way to express it down below. For here, we have 1 row, 2 rows, 3 rows. So this is a 3 multiplied, or 3 by. The little multiply symbol means by. And I have 1 column, 2 columns, 3 columns, 4 columns. So again, when we're counting the size of an array, which we'll get to that, the quote-unquote size of the array is known as the order, but we'll see that again in a moment. So the order is the number of rows by the number of columns. So I'm going to provide a brief definition and a general structure for all matrices. So we got definition. Oops. So a matrix, the plural is matrices, is a rectangular array of numbers written within brackets. If you've taken computer science classes, you know that an array is a quote-unquote collection of data. Generally, you work with one-dimensional arrays in computer science, which would just be if we only had 1 row or 1 column in a matrix. A matrix is a 2-dimensional array since it has kind of a horizontal and a vertical aspect to it. And we have a generic way of labeling matrices. So we always start with A11, which is entry 11. Then we would go to A12. So we always work with the first row, so the row hasn't changed, so I'm still in 1. Then we skip some entries until we get to some A1J, which might be in like the middle of the matrix. And then we skip ahead to A1N. This is I'd say it's a formal way of expressing the number of columns in a matrix is with the number, or the letter N. We then go to row 2, which would be A21, A22, all the way to A2J, and then to A2N. We skip some elements. We're going to go to AI. So this is just some random entry within a row. So this is maybe it's row 3, maybe it's row 4. So J, I'm going to actually write this below. So columns. We usually associate columns with the letters J and N. And rows, well, we see I right now. By the way, I is before J in the alphabet. Unless you're me, you say it backwards. So we have I. I is before, right? Yeah, I, J, okay. So if I is before J, we're probably going to take the letter before N, which is going to be M. So then we have AI2 all the way, this is continue down, AIJ, AIN, and then we'll finish off our matrix by going to AM1, AM2, so this would be the final row. M always represents the last row of your matrix. AMJ, and this one is AMN. This is just the general structure of a matrix. We might have a 3x4 like here, we might have a 3x3. We might have, if you're doing a lot of data, you might have, say, a 100 by 3 array. If you had, say, like 100 participants in a survey and you're gathering their age, height, and weight. And I should be able to fit this. So continuing with this, so each number, I have to remember how to write in subscript. I don't remember if I can in here. So I'm going to fill this in a moment. Don't copy it just yet. So it should say each number AIJ. I can't do subscripts in this, so I have to physically write them. So each number AIJ is called an entry or an element. The first subscript I is the row index, which we saw kind of on the right side right now. So J is the column index. There are M rows and N columns. So its order, which is also like a proper name for size, is M by N. And I need to go write the IJ. I believe actually I can set this to cycle my layers. Oh, that's even better. Okay, so we have our definition now of a matrix. We've seen a few examples. We're going to keep looking at other types of matrices and things we can do with matrices. So I'm going to scroll on up and over. First and foremost, I'm going to keep using text. So when M is equal to N, which we saw in example 1, so here I had like a 3 by 3. We call this a, if you want to try and take a guess right now at what shape matrix we would call this, feel free to. Shape A. While I finish typing this. So hopefully you recognized, oh, if one side is equal to the other, we would call this a square matrix. So this is just using linguistics that we've seen in mathematics before. When M is equal to 1, that means we only have one row. So it's just called a row matrix. And last but not least, when N is equal to 1, well, in this case, we'd only have one column. So this is just called a column matrix. And then from here, we'll look at some quick examples and then move on to additional stuff. So right now this is again just introducing matrices. If it's lighter, good. It should feel like lighter material. That means that this is successfully a lighter section. 2, 1. I'm actually going to pause this real quick and just finish writing these. Okay, so I have a few examples up. We're just going to identify the order of each. In this first case, we have 2 rows. So I have 1, 2 by 2 columns. So this is a 2 by 2. I'm actually going to do this in a different color. Oh, and I just changed my language. 2 by 2. We have a 2 by 2 matrix, which is also square. I never finished writing my bracket. In this case, we have 2 rows, 3 columns. So this is a 2 by 3. This one we notice that we can have negatives in our matrix. For here, we have 3 rows by 3 columns. We even have a negative fraction. So this one is also square. In this guy, we have 1 row by 4 columns. So this is a row matrix. And here we have 4 rows and 1 column. So this is a row matrix. Column matrix, not row. We have 1 column, so it's a column matrix. Okay. Now we can have different types of matrices, and this one is where it gets important for what we've been doing. If I had, and this is tying now into what we've been doing in 8.1 and 8.2, if I had a system of equations, so if I had 3x plus 4y equals 1, x minus 2, y is equal to 7, I can still represent this where each row would be an equation and each column would be a variable or the solution. To represent these, I always have to have my variables on the left and I have to have my constant on the right, and we use what is known as an augmented matrix. And we're going to see the example really quick. So here I have 3, this should be 4y, as my x coefficient. So all I do is write the x coefficient. I don't bring the variable in. So I have a 3, a 4 for my y, and I have 1 as my solution or my constant. In equation 2, so row 2, I have a 1 for x, I have a negative 2 for y, and I have a 7 for my constant. The only thing different about an augmented matrix is it shows an equation, which means we have to have the equals sign represented somehow. And to do that, we just draw a solid line before the column that shows your solutions. That's it. Nothing fancy. You just do what you normally do and then draw a line so that you always want to have your answers in the rightmost column, and you draw a line before it to show the equal sign. So the vertical line means equals. I could do this for some other examples. So if I had x minus y plus z equal to 2, 2x plus 2y minus 3z is equal to negative 3, and x plus y plus z is equal to 6. So for here, again, all we do is write the coefficients. X has a coefficient of 1. Y has a negative 1 coefficient. z has a coefficient of 1. I'm going to draw my vertical line already because I know this is my equal sign, and it equals 2. Equation 2, x has a coefficient of 2, y has a coefficient of 2, z has a coefficient of -3, and it equals -3. Equation 3, x has a coefficient of 1, y has a coefficient of 1, z has a coefficient of 1, and it equals 6. One more, and then I have to actually start a new page. I've been writing a lot bigger today. Hopefully that will make the notes clearer when I post them in the notebook. So x plus y. And this is, again, to show we don't always have to have the same number of equations as we do variables. So I have x plus y plus z is equal to 0. I have 3x plus 2y minus z is equal to 2. So here, my equation 1, x has a coefficient of 1, y has a coefficient of 1, z has a coefficient of 1, and it equals 0. For equation 2, x has a coefficient of 3, y has a coefficient of 2, z has a coefficient of -1, and it equals 2. So I've now turned systems of equations into augmented matrices. I'm going to actually let this sit here for a moment while I go make a new page. So this is video, I think this is video 12, page 2. I'm also going to save this one really quick. Am I in pre-calc? I'm in algebra right now. Alright, I got the other page saved. So we're going to start picking up from here. And how we can actually, we're not going to, I don't think, no we did. We're going to start to see how we can solve for systems of equations when they are given to us in matrix form. Which means I'm actually going to write some notes first, but then we have to define some operations we can do. So 8.3 Intro to Matrices. This is on augmented matrices. This is kind of large. So things about augmented matrices, what we do know about them. So each row, as I was saying, is each row is a column. The vertical line is our equal sign. Column 1 is our x variable. Column 2 is our y. This is just our standard notation for when we're working with matrices to represent. Right now we've only gone up to 3 variables, so this is for representing 3 variable equations. If it was a 2 variable equation, it would stop at column 2 being y. Column 3 is our z. And last but not least, if a variable is not in an equation, then the coefficient, I'm going to use the vocab word entry, is 0. And then we also need to know what are some row operations we are allowed to do. This is how we can start working to solve a system of equations when given to us in matrix form. It's also how we can work with matrices in general. So first and foremost, we did this in 8.2, where I was saying, hey, if we're solving a system, let's just switch the order of our equations. So the first row operation we're allowed to do is interchanging rows. This is perfectly fine. There's nothing wrong with it. All of these operations, I'm going to write this. So all operations yield an equivalent augmented. We don't have to necessarily say augmented matrix. So yield an equivalent matrix. So interchanging two rows, the matrix, even though it might look different, it still means the same thing to us. And our way to denote this is row. I'm going to swiftly change this to a smaller font. So row 1. Oops. Is switched with row 2, for example. Our second operation is multiplying an entire row by a constant. This includes what's on the right of our vertical line. I'm actually going to tab this out. So this would be represented by a constant c times row 1. I'm going to put that in afterwards. Goes to row. Actually, I want this to be row I. Doesn't have to be rows 1 and 2. I want this as a generic statement. I would use I, so I'm going to go back and just fix this here. So this should be an I, and this should be a J. So I'm just switching any two rows. For here I'm taking a constant, multiplying it by a row, and putting it back into the same row. And then the last thing we can do is add a multiple of one row to another. So I could do C times row I, I'm going to leave that for a moment, plus row J, and put that into row J. So this needs to be a J. So whatever row you are multiplying by the constant is not the row you are changing. So again, I can interchange, say, row I and row J. That gives me an equivalent matrix. I can multiply an entire row by a constant. That will give me an equivalent matrix. I can add a constant, I can add a multiple of one row to another row. So I could take C times Ri, add it to Rj, put it back into row J, and get an equivalent matrix. We're going to do an example. I'll give you 2 to try on your own, and then we are all set. So I need my brush. I'm going to go add a new layer. So I'm starting with Just some examples. So here's 2, negative 1, 0, 2, 3, 1. So if I wanted to switch, just to denote this, row 1 and row 2, I would, well, row 1 is now going to become row 2. Row 2 is 0, 2, 1. Row 2 now becomes row 1. Row 1 was 2, negative 1, 3. All I was doing here was just changing the order I wrote two equations, which is fine. So this is one example. Another example would be negative 1, 0, 1, negative 2, 3, negative 1, 2, which is equal to 3, 0, 1, 3, and is equal to 1. If I wanted to do, say, 2 times row 3, and make that my new row 3, I would keep every other row, no other row changed, so I don't need to worry about those. So row 1 stays the same, row 2 stays the same. Row 3 I now need to multiply by 2. 0 times 2 is 0, 1 times 2 is 2, 3 times 2 is 6, 1 times 2 is 2. Then we have I'm actually going to skip one of them. Or actually, no, I'm going to do both. Just because I want to show that we can multiply by a negative. So this is 1, 2, 0, 2 is equal to 2. Then 0, 1, 2, 3 equal to x. I can multiply rows by a negative constant. So instead of being instead of being like constant times row 1 plus our row 2, it'll be row 1 minus 2 times row 2. Row 2 is my one that's being multiplied, so I'm going to be putting this into row 1. I don't know why I wrote an x here. This should have been a 5. So this operation, I'm starting with row 1. Row 1 is changing. So I'm going to do 1 minus 2 times 0. 2 times 0 is 0, so I still have a 1. I'm going to have 2 minus 2 times 1 is 2. So it's going to become a 0. I'm going to have 0 minus 2 times 2 is 4. This will be a negative 4. I'm going to have 2 minus 2 times 3 is 6. So this is going to be a negative 4. I'm going to have a 2. There's going to be 2 times, or minus 2 times 5 is 10. So this will be equal to negative 8. Only row 1 was changing, so I can just copy row 2 into my new augmented matrix. And I'm done. That solved this row operation. And then last but not least, and this one will actually then solve for the system, I could have 1, 0, negative 2 is negative 3, 0, 1, 2, 3 0, 0, 1 times, 0, 0, 1 equals 2. I could do row 1 plus 2 times row 3 is going to become my new row 1. So I'm multiplying row 3 by a constant, I'm adding it to row 1, so row 1 is what I'm changing. So 1 plus 2 times 0 is 0, so this is just going to be 1. 0 plus 0, this is going to be 0 still. Negative 2 plus 2 times 1 is 2. So I have negative 2 plus 2 is 0. I'm going to have negative 3. So negative 3 plus 2 times 2 is 4 is just 1. I'm not changing row 2 and I'm not changing row 3, so I'm just going to copy what they are. And then 0, 0, 1, 2. I can now translate this back into a system of equations. So for equation, or row 1, this is my equation 1. I have 1x plus 0y plus 0z equals 1. For row 2, I have the equation 0x plus 1y plus 2z is equal to 1. Sorry, is equal to 3. And for my last row, I have 0x plus 0y plus 1z is equal to 2. So from this equation 1, I get x equals 1. From equation 3, I get z equals 2. From equation 2, I have y is equal to 2. Y not is equal to y plus 2 times z is 2 is equal to 3. So this is going to be y plus 4 is equal to 3, but then I can just subtract 4. So I'm going to get y is equal to negative 1. So my solution would be 1, negative 1, 2. So matrices are another way to show systems of equations. They're extremely useful, really, in life. Anytime you're working with a tabular format, you're really working with a matrix. These are the basic operations. I'm going to scroll back up in a moment. Actually, I'm going to zoom out. I don't know why Alt didn't work. So again, the basic operations are we can just change 2 rows. We can multiply an entire row by a constant. We can add a multiple of one row to another. And those are our 3 basic operations that we can always use on matrices. So for just a slight activity, just try writing these 2 systems as augmented matrices. That's all I'm asking for. I'll see you all again hopefully next Monday.